thank you very much, Shaw. Hi, everyone. So thanks for the introduction. So I'll go directly to the presentation and to our study. So today I'll be presenting you a bit more details about SPSA. So it's the weighted simultaneous perturbation stochastic approximation, which is an algorithm that we've been using a lot in the calibration of simulators. And this work is focused on more the practical aspects and the computation of the weight matrices and how it should be designed for different applications for traffic simulation models. Although SPSA can be applied to other calibrations of other types of systems. So this work was initiated a few years ago at MIT with research from Lulu that now is in Google, which is he's the third author, and the continuation of this work has been led by Professor Antoniou. So he's from NTUA in Athens, Greece, and this paper he's the first author. Unfortunately, he's traveling today. And the other two authors, Francisco and Moshe Ben Akiva, are based at MIT. Francisco actually is now in Denmark, just moved to DTU University. So let me try to, okay. So the outline for today, if you have any questions, please post on the chat. I'll try to address them right away if it's useful for the audience. So the outline today, I'll give a brief introduction on the problem itself and what motivated us. I have to go through a bit of notation and to explain how SPSA works, and the introduction of the SPSA, which is quite a straightforward but smart changes to the algorithm to make it more efficient. And then I'll focus on the estimation of the weight matrices, which is one of the features of the SPSA. And I'll present you the results of its application to two different case studies. One, which is a dynamic traffic assignment for a case study in Singapore, and the second one, which is the calibration of a microscopic traffic simulator for a smaller network in Portugal. Then I'll briefly give some conclusions and the conclusions that we got from our study and what we are working on at this point, and I'll open the floor to further questions that you might have. So the challenge, most of you know already that simulation tools are used to test the design of different technologies when we cannot test them in the field, so that's useful, and that's widely used nowadays for not only for practice but also as a research tool for different kind of applications. Now the challenge is that the calibration of all supply and demand parameters of traffic simulation tools is quite difficult, typically because of the number of parameters and the unknown search space during the calibration. This is mainly due to the complexity of the models and also in the way they are designed. So typically, for example, most of the traffic simulation tools use dynamic OD matrices as an input, and this has a large number, typically a large size of data that needs to be calibrated. Now on the other side, the constraints is obviously computational costs, and the lack of analytical models when we are facing extremely large networks. So these, among others, so that's these challenge and these difficulties was what motivated researchers to develop a set of non-analytical algorithms for the calibration of such tools. One of them is the simultaneous perturbation stochastic approximation. So this was developed initially in the late or the beginning of the 90s, and it started to be applied in transportation 10 years ago. So we can find already several case studies. I've mentioned it here, a few of them. I can briefly tell you how they were used for. So, for example, in Balakrishna, he was one of the initial and managed to show the difference and the benefits from using SPSA compared to the regular finite differences and other non-simultaneous perturbation models. Ma and his peers compared the performance of SPSA against two other different algorithms. One was genetic algorithms and a trial and error iterative adjustment algorithm for the calibration of a microscopic traffic simulation model in Northern California. Then Lee and Kanosbai proposed a Bayesian calibration method and applied a slightly modified SPSA algorithm to solve the calibration problem of a cell transmission traffic model. And finally, let's say in the last years, it was spread to core sim, for example, in the study of PAS, and also in use for the calibration of Artemis, and also the study of emissions models or emissions outputs, let's say. And now, before going to the benefits of the WSPSA, I'll first go through some notation and details about the original SPSA algorithm. So the idea here is that we want to minimize a specific function, error function typically, which is called Z here, and we want to minimize it depending by changing the, let's say, static parameters and time-dependent parameters, typically from our simulation model. And this is done by, having the error function Z by having different kind of components. So we have the observed time-dependent measurements. So these are the measurements that we want to compare with. We have our simulated time-dependent measures, or basically the output of our simulator. It's given here by M, S. Then we have the parameters that we want to calibrate already, so the static and the time-dependent parameters, so beta and X. And then we can have a priori estimates for both of this set of parameters, so both for the time-dependent, so typically when I mean time-dependent are the ODs for the case of traffic. And static parameters can be the supply parameters or, for example, the driving behavior parameters. And we can have a priori estimates from previous studies. Now, this problem formulation has constraints, and we have basically the constraint of the simulated time-dependent measurements that are given by our simulator F, so which has as input the time-dependent parameters, the X, the static parameters beta, and fixed parameters like, for example, the road network topology. And then we can set constraints on like lower and upper bounds to our parameters that we want to calibrate. So, for example, like if X is a specific OD flow, it should be bounded by 0, it cannot be negative. And we might have some insights on how, let's say, reaction time parameter, so a specific beta parameter, it cannot have also, different values. So, under the generalized least square assumption, how typically this problem is specified is by summing up over all the time. So H here is each time window, or each definition of time period, let's say. So if we have a dynamic origin and destination matrix in the X input variables that we want to calibrate, H will be the number of times that we divide the OD matrix. And then typically how we do is we sum up the errors, which are denoted here by eta, which are the differences between the observed and the simulated values. And we use the omega as the variance covariance matrix. And that's how typically we write down the problem formulation under the generalized least square expansion. So from now, what changes in the generalized formulation in the bottom of the slide is how it's specified under the GLS and how beta and x are put together and called theta. So that's our parameters that we need to calibrate. It's just theta, which is a combination of x and beta. So how stochastic approximation algorithms are iterative stochastic optimization algorithms when the objective function has no known analytical form. So one typical case is what we call sometimes the black box approach. So we cannot identify the f function at the beginning of the slide because it's stochastic and is given by a simulator. So we can only estimate the gradient with Gaussian observations when we are doing our algorithm for our optimization. So what SPSA does is, so at each iteration, and here each iteration is denoted by k, we reduce the variation depending on the gradient estimated value, which is denoted here by g. And AK, it's called, it's a step-based parameter that typically gets smaller as the number of iterations k is larger. Yes? Any question?
Maybe not. Okay. You can go ahead. Yeah.
So AK is typically called the step size in the gain sequence. So this idea where we is derived from the finite differences stochastic approximation. So where the gradient is estimated by perturbing the parameters in the decision vector one at a time, and we evaluate the objective function values. And so each parameter is typically perturbed with an amplitude of ck. So that's the third equation in the slide. So again, we have the values of the parameters of the previous iteration of our algorithm. We changed their values with ck delta k, and delta k is computed at each iteration as well. And so we can compute the differences between the variation of this value for each side of each original value for each iteration, and we can compute the gradient accordingly with the finite differences. So the way you operate typically the SPSA algorithm, and this maybe will make things a little bit more clear, is that we start by setting the current time step, the current algorithm step by k equal to 0, and our initial values for our parameters to be calibrated are set to their a priori values. And we also decide on the values of the SPSA algorithm itself, which in this case are the parameters of that define AK, which is the small a, the big A, and the alpha. So then we can compute the value of the initial objective function for Z0. This means we can run our first simulation, and we can see how far are we from the observed values. And then we start the algorithm in an iterative manner. So we update the step size, we calculate the new AK and the CK, and then we generate independent random perturbation vectors for our estimation of the gradient. And then we can evaluate the objective function at two different points. So when we perturb the parameters by a plus value and a minus value, then we check for the boundaries of our constraints, and then we can estimate the approximation of our gradient vector using the previous formula. We can compute the new value of the parameters given the approximation of the gradient, and if it's converging, we can, to a specific value that we define, we can stop the process. Otherwise, we go back to step 3. So now, what is the problem with this SPSA algorithm? So the reason for the performance deterioration of the SPSA was found to be related to a gradient approximation error that increased rapidly with the problem scale. This means that the source of the error was not the stochasticity in the simulation tool, nor the inconsistency in the observed data due to measurement error, but the way SPSA is estimating the gradients. So the problem is that at each iteration, the gradient estimation process essentially tries to find the direction and amplitude for each parameter value in the decision vector to move. This is achieved by comparing the influence to the system caused by perturbing each of the parameter values in the two opposed directions I was showing before. The problem is that the influence caused by perturbing the value of a specific parameter is determined by a scalar. And that is clear, for example, in this example that I have here in this slide. And the scalar is typically the sum of all the distances between model outputs and corresponding observed measurements. So because you are perturbing the parameters at the same time, you cannot capture the relationship between each parameter and the actual differences of the measurements that you are computing at the end of our iteration. So in this way, eventually is not a big problem in the systems where each parameter is actually highly correlated with most of the measurements, because in that case, the change in each parameter is responsible for the change of almost every measurement value, which is okay. But that's not what happens typically in large transportation networks. So an example here is if we assume the variance covariance matrices from the previous slide, that for the measurements it's equal to the identity matrix, and for the a priori parameters it's 0. So we ignore the deviation, so we don't care about the deviations of the current value of the parameters and a priori values in our calibration. And we assume, by assuming the identity matrix for the measurements variance covariance matrix, we assume that the values, or we assume the relationship in an ordinary least squares. If we use these two assumptions, then the value of the error function z is given by basically the sum over all measurements d of the deviation, the square of the deviations. And if we use this error function z, then you will see that if we use the formulation of the SPSA, this is the formula of the gradient approximation. And the important thing you have to note is that in the numerator, so in the top part of the equation, it does not depend on I. So what this means is that the numerator does not depend, the scale of the numerator does not depend on the parameter I itself, on the variation of the delta of the parameter I. So basically, that's why there is this lack of relationship between the numerator and the denominator, that we cannot make this link, and therefore is not efficient. So what WSPSA does is that it excludes the negative influence of irrelevant measurements in the gradient approximation of SPSA by introducing a weight matrix W. So for a change in a parameter, we introduce just a little weight in the equation, and that represents the relative magnitude of change in measurement J. So basically it brings the relationship between measurement J and the parameter I. And basically rewritten the new equation of the approximation of the gradient, and then we can see that this relationship appears in the numerator. So first of all, what does how can we estimate this W? So this very empty slide, we show that basically it's a straightforward concept where the measurements can be obtained directly from the adjusted Jacobian matrix J. And this means that each element of the matrix replaced in the Jacobian matrix. When I say by the adjusted Jacobian matrix, it means that each element is replaced by the absolute value from the traditional Jacobian matrix. And why the absolute value is just because we are interested in the magnitude in this problem. So the relationship of the weight between GI can be the the relationship or the differences between specific measurement J and what was the perturbancy of the parameter I. So typically, when we are going through online calibration problems, we have highly nonlinear, and the Jacobian matrix may change, typically changes with current parameter values. And this means that the weight matrix should be re-estimated during the calibration process itself, along with the change of current estimated parameter values. Now, the frequency for updating the weight matrix depends on the specific problem or on the stage of the calibration problem as well. So that if there is small variations going forward in the algorithm, eventually the updates of the matrix doesn't need to be as frequent. So it was shown previously, and I have just an image from the first paper where the SPSA was proposed, and that the comparison between the SPSA and the SPSA was proven to be very beneficial. And so the convergency was much faster with the SPSA. Now, how can we, in our problems, estimate this relationship between the measurements and the parameters? So we proposed in this paper that we presented at ISTTT, we proposed 5 different methods. So the first one is the analytical derivation, which is easy to understand but very hard to do. Here, typically, it relies on the direct observation of parameter measurements relationships, and we can formulate them, so we can use it directly in the algorithm. And the more observable the system is, the less complex the problem may become. So it's the more faster is the algorithm, let's say. Now the difficulty is that for this analytical derivation, we need to know the relationship that depends on the network topology, the path choice set, the equilibrium link travel times, and the root choice models, and we need to formulate it accordingly. And for large networks, typically this is not trivial. Although for small networks, it was shown that this can be formulated. The second approach, though, it's typically what's easier to compute. So we can, and especially when we are dealing with origin and destination matrices. So the simulation tool can be used to compute a weight matrix approximation. And a good example is the assignment matrix, which is endogenous to the simulation model itself and cannot be analytically estimated. So we can rely on the simulation tool to give us an estimate of the assignment matrix for each time step of our algorithm, or for each origin and destination values. So the entire process may be initiated using one-step predicted OD flows generated at the end of the previous interval, or using just a sieve OD matrix. So typically a point that I wanted to note here is that when we are estimating the assignment matrix from the simulator, we should always use multiple replications because of the stochasticity nature of our simulators. And from the multiple outputs that we get from the multiple replications, we just have to find a way, or a combination, or a linear combination, to estimate the weight matrix for that specific time step. A third way, and it's very similar to the previous one, it's the numerical approximation, where at each iteration of our algorithm, besides during replication for given OD. So we have to run multiple replications. We can generate some numerical experiments where the OD is actually not the same, but close, different ODs close to the point where we are now in the algorithm. But we can estimate the weight matrix depending on different values of the initial parameters. So we have to generate the experiments. So for example, if we have a specific value of origin and destination flow, we can add a small perturbances on the origin, and that's that specific origin and destination flow. That will be the delta Ni, will be with one perturbation and then another perturbation again. Finally, we have the heuristics-based approximation. So here is that we do assumptions regarding the weights or the relationship between the measurements and the parameters. A typical example is for the driving behavior parameters, where they eventually might affect all the measurements in the network, and we just assume that the weight is 1. Finally, the hybrid and composite methods is if we have multiple ways to compute these weights, we can combine them through some again, linear combination for the hybrid, or we can decide that parts of our weight matrix will be defined by one specific method, and other parts of the weight matrix will be given by a second method. And this was the examples that I'll show you next. The composite method was actually what was adopted, and I'll explain you briefly why. So for the first example, the case study was a large-scale mesoscopic dynamic traffic assignment. It's a free software developed at MIT called DynaMIT. It's a simulation-based mesoscopic DTA for demand and supply. So we have a formulation of the demand mesoscopic, and the same thing for the supply. So the demand is based on a path size logic for root choice and the dynamic OD for different time periods. And the supply is based on 2 different models. So one for a moving part of a link is given by speed density functions, and the second part is a queuing part that is which has parameter for capacity. In the figure above, you can see the entire road network for Singapore, and what we did was we selected just the expressways for Singapore, which count of a total of about 3,400 segments and 4,000 OD pairs. So in terms of problem size, we started with a simulation only for 3 hours, but with a dynamic OD by every 5 minutes. So this results in a total of about 150,000 time-dependent OD flows. So these are our parameters that need to be calibrated. Our X variable from the previous slides. Then we have one root choice model parameter. So this was the root choice model parameter has more parameters, but we selected only one, which is based on travel time, which is a travel time parameter. So what's the importance in root choice, depending on the travel time importance in root choice. And on the supply side, we had 6 speed density function parameters for each segment, and 1 capacity parameter. So this ends in a total of almost 24,000 parameters, or let's say static parameters, as I mentioned at the beginning. In terms of measurements, and after cleaning the real networks, the real counts, sorry, we had 216 measurement locations, and we had counts, average counts and speeds for August 2011. And the 36 is because of the time. We had the measurements for every 5 minutes during those 3 hours for the morning peak of Singapore. The composite method that we use is we estimated the weight for the relationship between OD and counts from a simulation approximation. So we got it directly from DynaMIT, and at each iteration we updated the weights. And we assumed for the supply parameters and this, for both counts and speeds was based on heuristics. So here, if the measurement that we are interested so the value of the weight between the parameters of a specific segment and the counts that are collected in that segment is 1, and for all the rest is 0. So that was the assumption. And the results here is the RMSN for both counts and speeds at the initial, so using the seed OD that we got from previous estimations, and after doing the calibration for the 3 hours of simulation. The second case study was regarding a microscopic traffic simulator, which is open source. It's called MISTIM, and the objective was to calibrate the simulator for a large set of scenarios targeting surrogate safety analysis. So here the idea was we need to generate simulated data for several situations, so for several time periods, several conditions. And so we need a fast way to, manage to calibrate all those situations. By situations was a total of more than 6,500 scenarios, so simulation instances. So we need to calibrate each of them. The network was a small highway, about 5 kilometers in the north of Portugal, and we had only 100 OD pairs as input. For the supply, and I think it's in the next slide, yes. So we had, the idea was to, for each of the scenarios, we need to simulate just 30 minutes because we're focusing on specific periods of the day. And we had dynamic OD by 15 minutes for each scenario. So basically it was 2 periods, which results in 200 time-dependent OD flows. We've selected from previous sensitivity analysis 11 driving behavior parameters that are related to acceleration, lane change, and reaction time. And we had data for 192 sensor measurements on the network. So again, we used a composite method. In the same way for the relationship between the ODs and the measurements, we got it from MISTIM. Using an estimated assignment matrix by the simulator from what was observed in the simulation. For the driving behavior, we assumed all the parameters, the weight of those parameters was 1, and it was the OLS assumption was assumed, so the variance covariance were block diagonal in the first equation that I showed. And so in this graph, we see for the 6,500 calibrations that we had to run, so it's different from the first case study where we only did 1 calibration. Here we had to do 6,500. We see the distribution reduction of the RMSN for both counts and speeds. So you can see that the majority of the reductions are between 20 and 60% on the RMSN. There is a better, let's say, a better match for the counts because the assignment matrices were the weight matrix for the speeds was used the same as the counts. So basically, it was the assignment matrix used for both the relationship between ODs and both speeds and counts. So to wrap up. So we've presented alternative methods to estimate the weight matrix. Heuristics and composite methods can extend its applicability, so that the flexible way that we can specify how to compute the weight. It's a big advantage in the way we formulated in this paper, and we showed it with 2 different case studies with very different nature and models. And obviously there is a very important aspect on the definition of the boundaries during the calibration. So from our experience, we understand that the convergence can get much faster if the boundaries are well set, but this is not new. In terms of research streams that we are doing is we are trying to, within the algorithm, to change a few things. So the ratio of the perturbation. So typically, the perturbation is generated with a random process, both on SPSA and WSPSA. And we are testing if we have different process of the generation of the perturbation at the beginning or at the end of the algorithm, if the convergence can get better. The same thing as a selective perturbation. For example, if we have, or we know already that the initial values of our parameters are below or are underestimated because the pseudo-D was very old from what we expect now, we can select the way the direction of the perturbation right at the start, so to make it more faster at the beginning. And we can also select, so far we are doing the perturbation simultaneously for all parameters. And we can actually have a simultaneous perturbation on a specific subset. Finally, the aim also is to start using it. So far, we only have been doing experiments offline, and we are now trying to do it on an online calibration to see how this, if the gains in performance that we managed to get with the WSPSA are enough to make it useful for online applications. So that's it. Thank you all for the attention.
Thank you, Carlos, for your nice presentation. I learned a lot. So for all the audience, if you have questions, comments, suggestions, anything, please feel free to share them among us. So now you can unmute yourself if you want to speak out, or you may just leave your messages or questions on the chat box.
Was there anything that was not very clear, specifically?
Right. Yeah, if you need clarification or anything, yeah, you may also raise your questions. So let's just wait a little bit, see if anyone would like to be engaged in a discussion. Okay, so Carlos, I guess you received a question from Michael Mehat. It's shown on the chat box, and do you want to address that? Or so the question is, what kind of analysis have you done of the actual changes to the parameters? For example, the link performance parameters that were made by the calibration processes. He said he came late to the webinar, and so he might miss anything. It's a good question.
Yes. So I'm guessing that the question is, after we did the calibration and we reached to some values of the, for example, on the supply side, if we did any kind of sensitivity to it. Okay, there were a few. First thought, and it might not be related to your question, but eventually might worth to point out, is that there are also algorithms of the SPSA itself. There are parameters in the SPSA itself that were previously in the initial paper that were tested. Because we have to specify in the both SPSA and WSPSA, we have specify some values of the step size, for example. And so these were tested with different values at the beginning. And actually, for both the simulators, for both for the DynaMIT case study and for the MISTIM case study as well. For the values at the end, we didn't do any kind of test to the final values. We just, if they are within the bounds that we specified previously from in the computation, but it's very interesting because there's weaknesses in the way we've specified the weight matrix for the supply side, because it was a very simplistic approach for the DynaMIT case, where we said that only the measurements that are within the specific segment, we assume the weight to be 1 and all the others to be 0, which ignores some kind of geographic correlations between the sensors and the measurements, for example. So that is something that we should still test, for example. I don't know if I answered your question properly.
There might be a follow-up question. Not sure if that's addressed.
Oh.
Oh
yes, yeah. There were. So, Michael, yeah. So let me go back. So, for example, in the formulation, there are bounds to each of the parameters, both on the supply and the ODs. So let me try to go back. It's in the initial part of. Oh, there you go. Oh, here it's. So yes, so when we specify the problem formulation, we have bounds for both the ODs, which are the X, and for the supply parameters, which are the betas. So typically, for example, for the driving behavior parameters, we've collected previous calibrations for the MISTIM simulator, and we've created a distribution. We've enlarged the bounds, and that was our lower and upper bound. And plus, having negative reaction times, and these things were set in the constraints. And similar for the speed density functions. And by the way, one of what we are doing now, for example, is having bounds for different categories of segments. So we are trying to make it a little bit more easy to specify. So we have we can have bounds for arterials, bounds for freeways. So that's our approach now, to make sure that that the results are more consistent at the end. Thanks for the question, Mikael.
Okay. Is there any further questions? Okay, I guess I thinking somewhere on the chat box I sent to you the contact information of Carlos. I'm gonna send that to you again in the end of the chat, so you can visit his webpage or email to him if you have further questions. With this, I guess I want to finally thank Carlos for his nice presentation, and I want to thank all of you for your attendance. I wish you all have a good holiday, and this year's webinar series are done, and I'm gonna see you next year. Next one will be January the 8th. So, well, thank you all of you. The meeting adjourns.